Hello everyone. We'd like to welcome you again to the Heidelberg Colloquium, and as you see over there, you can go to YouTube and put Astronomy Heidelberg in there, and you'll see all the colloquia there if you want. And it's our pleasure today to welcome Avery Broderick, and we passed a little bit at the CFA, same building, 2 floors apart, so we didn't see each other that often. But he got his PhD at Caltech, and then he moved to Harvard, and then he moved to CETA, that I'm supposed to mention. And now he's at the University of Waterloo and also at the other institute where he gets half of his funding, Pyramidal. We're supposed to mention that because that's the commercial part. Anyway, so he will tell us about black holes and horizon scales and what's new in the field.
Thank you very much. As long as the other end isn't attached to a bar above me, we're good. All right, so this afternoon I want to tell you a little bit about imaging supermassive black holes on scales comparable to their event horizons, and this is really an exciting time because I get to be honest. There really is more than one. And I'll talk a little bit about the other example near the end of my talk. But we're really entering an era where we can study black holes on scales commensurate with their event horizons. But before I get into how we do that and what we've learned, let me tell you why you should stop what you're doing and start studying black holes. And the first, probably best answer is that black holes are cool. And that's not just a bad physics joke. You know, it's a thing madmen fly their ships into. I know I'm getting old because I saw someone else put this picture up and said, does anyone in the room know what movie this came from? And I did. I was like, oh man. They're also something rock bands write albums, popular albums about. That's nice. The plot device that second-rate directors ruin beloved franchises with. Yeah, that's the new Star Trek movie. And if you leave astrophysics, you can have a lucrative career writing economics textbooks. Apparently, that's the second most common thing on black holes on Amazon. Of course, there are good scientific reasons, too. And when I wear my astronomer's hat, I think about black holes as the engines of the cosmos. Okay, so here's a prototypical quasar. Luminosity is 10 to the 47 ergs per second, and they may be able to get 10 to 100 times brighter than that. Not only does luminosity come out in the form of photons, but sometimes it comes out kinetically in the form of outflows. Here's an image of Cygnus A with these ultra-relativistic radio jets that can extend as far as megaparsecs in some cases. So truly the distance between galaxies. And these are not without consequence. If you look at galaxy clusters, here's a picture of the hot X-ray emitting gas in the intercluster medium, shown in this blue, superimposed with the red emission from the radio, presumably these radio jets. And you can see these jets are excavating large cavities, galaxy-sized cavities in the intercluster medium, and limiting how much gas can fall down and accrete onto galaxies, and controlling what those galaxies end up looking like. So if you really want to understand why the universe looks the way it does today, you have to understand how these jets are launched, presumably from right around the black hole, and how all that emission comes out. And perhaps even more mystifying, not only do they have such large impacts on this area around them, but some of them, in fact most of them, don't shine at all. Here's a picture of the black hole at the center of our galaxy, and if you can find it, your eyes are better than mine. It's overwhelmed by all the stars in its vicinity. So astronomically, why would we be interested in black holes? Well, the two, I think, big questions amongst many are why do some of them shine and others not? What controls when a black hole is active and when it's not? And how do they launch these all-important kinetic outflows, these ultra-relativistic jets? And why do some do this and others not? When I wear my physicist hat, and I spent half my time at this Perimeter Institute for Theoretical Physics, so I'm contractually obligated to be a physicist half the time. The reasons to study black holes really have to do with testing general relativity, doing what I call bookending GR. Okay, so what do I mean by that? The past century, GR has been amazingly successful. And here are a bunch of images from Cliff Will's nice review on these tests, on living reviews. Here's a list of some of the famous experiments, and it's been a spectacular success. It's passed all with flying colors. But the important thing to remember here is that all of these were in the weak potential limit, in the perturbative limit, when general relativity makes only small corrections. Even things like binary pulsars are in this perturbative limit. Okay. Testing it in the nonlinear limit, when this ratio, gm over rc squared, is of order unity, is much harder. And there are really only two places you can do this. The first is by making the mass very, very large. And that occurs on cosmological scales. You can plug in typical numbers, you find it's of order unity, or you can just recognize that this is really the Friedmann equation in approximate form. Okay, and this just says that GR is important to determining how the universe evolves on large scales. And what do we find when you try to probe general relativity on cosmological scales? It's that it's a spectacular failure. You need to invent 95% of the universe to make sense of it. And that 95% is the price of general relativity. Okay? I'm not saying dark matter and dark energy aren't there, but when my cosmologist friends try to answer what are the dark components, what they're really doing is assuming GR and trying to make the universe safe for general relativity. And there's certainly people, especially at a place like Perimeter, who are thinking about ways to fix general relativity and not add 95% of dark stuff. So certainly there's some evidence that maybe when we get into these nonlinear regimes, interesting things are happening. The other place you might look for where this is of order unity is for when objects are very compact, when this R is very small. And the most extreme of those is right near black hole horizons. Okay, and what do we know about those? Well, surprisingly little. And that means that we can't answer some very basic questions, things like, do they exist? Are there really surfaces that separate parts of the universe from causal contact with the rest? Do compact horizons exist? And if they do exist, is the strong gravity in their vicinity? Right in their immediate vicinity, really well described by general relativity. And by that, I mean, do the no-hair theorems hold? Is there a metric that I can write down that depends only on mass, angular momentum, maybe electric charge, although that's probably not astrophysically important. And that gives me a bunch of dynamical features which are robust and describe things going on around the black hole. And of course, once we have these two categories of questions, the astronomical questions and physical questions, it's natural to ask, how do the answers to one impact the answers to the other? How might mass and spin imprint themselves on the astronomical things we've been studying for 50 years? And vice versa, how can we try to infer properties of the black hole from the stuff we see? So these are the kind of the fundamental questions that push at least what I do on black hole science. And one of the things that unifies them is that their answers are all going to depend upon the physics right near the black hole horizon. And there are many ways people try to get at this stuff, try to get at what's going on near the black hole horizon, things like short timescale variability, looking at very high energy photons. I'm going to describe maybe the most direct way, just spatially resolve it. Okay, see where emission's coming from on scales comparable to the horizon size, and then based on that spatial resolution, discriminate between different possibilities. That's also necessarily the most ambitious, and the reason is because black holes, for all of their mass, are incredibly small. So here's a picture of a black hole accretion flow. I'll describe where this picture comes from a little bit later. The most important feature here is this shadow, this black interior. This is the shadow cast by the horizon on the surrounding luminous stuff. And it has a characteristic size, as seen from far away, of about 10 gm over c squared, about 5 Schwarzschild radii. And that's characteristic. That's just set by the strong gravitational lensing of light right around the horizon. This is the scale that you have to resolve. Okay? And even for the most massive black holes, their sizes are comparable to the sizes of solar systems. The black hole at the center of the Milky Way, it would easily fit within the orbit of Mercury. Okay? And the problem with that is in angular terms, in terms that are important for astronomy, these are quite small. So here's a plot of the angular diameter of this ring, here, for a number of known objects. And the largest in this picture is Sagittarius A Star, the black hole at the center of our galaxy. And it has an angular size of 50 microarcseconds. Next on the list is M87, about 40 microarcseconds. A cluster right around 1, maybe up to 10. But if you want to even think about making spatially resolved images of black holes, 50 microarcseconds is the number you have to reach. By way of comparison, all telescopes are at least diffraction limited. That means if I take my telescope that I look at with my daughters, look at stars and planets with my daughters out in the backyard, I'm diffraction limited at an angular scale of something like 600,000 microarc seconds. Even the biggest, best currently operating telescopes, things like the VLT and Keck, they're also diffraction limited thanks to adaptive optics. And if you search long and hard, you can find nice diffraction limited pictures. They really do make nice little airy patterns for the VLT. Keck are these hexagonal diffraction patterns because it has a funny shaped mirror. But even at the diffraction limit for these 10-meter class telescopes, we're talking about angular resolutions of 20,000 microarc seconds. Okay? Even for the next generation, what I like to call the superlative class of telescopes, because their names tend to include superlatives, like the giant Magellan telescope and the extra large telescope, and my favorite, the overwhelmingly large telescope, 2,000 microarc seconds. If you want to do this in the infrared, you need a telescope a kilometer across, not 100 meters. Okay, so it's not going to be done there. The answer is very long baseline interferometry. Okay, so the advantage of interferometry is that the diffraction limit is related to the wavelength divided by the separation between telescopes. It doesn't depend upon the size of individual telescopes. And so you can effectively make a very, very large telescope, telescopes the size of the Earth. And here's an example from the VLBA in North America. Of course, there's a European analog and now an Asian analog of the VLBA. And these have been operating now for many years. The bad news is that every pair of telescopes in this kind of array give you information about the Fourier transform of the image intensity map on the sky at exactly one point in that Fourier transform plane. And this is sort of important. Okay, so this means that the way you make a picture with something like this, with an interferometer, is you have many telescopes, and each pair measures a Fourier component of the image at exactly one point in that Fourier transform plane, this commonly called UV plane. And you fill in this UV plane with measurements of that Fourier transform. And when it's dense enough, when you have enough information in this UV plane, in this Fourier transform plane, to make a good approximation for the Fourier transform of the image, you invert it, and you make a nice picture. Okay, so that's how interferometry works. But that means you necessarily have to have many, many telescopes, many, many baselines. The ugly is, of course, this is all hard in practice for a variety of reasons. We don't really have to worry about them because really talented radio astronomers actually make this sort of thing work on somewhat routine timelines. Unfortunately, even the VLBA is not quite up to the challenge for imaging our horizons. The dishes in the VLBA operate above 3 millimeters, usually above 7 millimeters. And so that means that the highest resolutions they access are somewhere in the range of 100 to 300 microarc seconds. It's close, but still factors of a couple too big. Even worse, if you want to see that shadow of a horizon, you have to see through all the stuff in between us and the black hole. That means you have to see through the accretion flow itself, and you have to see through any junk in our galaxy, especially if you're talking about the black hole at the center of it. Okay, and at 3 millimeters, that's this orange region and into the green, orange and into the green, the spectrum of Sagittarius A Star shows this rising, characteristically optically thick branch. Okay, so the expectation is that Sagittarius A Star, this black hole at the center of our galaxy, would just appear to be a big ball, optically thick ball, when we're talking about 3 millimeter wavelengths and above. And similarly, scattering from electrons in the galaxy broaden the image in a highly wavelength-dependent way, and above a few millimeters, again, the size becomes dominated by scattering. So even if you were to extend the size of the Earth, put VLBA stations out in space, which actually has been done, you still would not be able to image the galactic center with something like the VLBA. Now that sounds very pessimistic because I've just spent the last few minutes telling you about things that don't work, but this really is great because it almost works. It's factors of a couple away from working. All right? It's in spitting distance. All we need is a version of the VLBA that operates at slightly smaller wavelengths. And that's what the Event Horizon Telescope is. Okay, it's a Earth-sized array of millimeter and submillimeter telescopes that either already exist or already are being built. And together, they access resolutions on the order of tens of microarc seconds. Okay, and remember, 50 microarc seconds was the target, so tens means we can put many pixels across that shadow. Okay? And there are a lot of reasons why you want to do this in the millimeter and submillimeter, but again, I don't really have to talk about them because a number of very talented people, including people at Max Planck, have actually got this to work. Here's an image of those visibilities of that Fourier transform amplitude of the intensity map shown for a handful of positions in this UV plane. Here it's just along one line. And you can see that there's a drop. And this drop is characteristic of structure in the source on scales of about 40 microarc seconds, less than the 50 of the horizon. So already in 2007, data was taken, published in 2008, of subhorizon structure in the black hole at the center of our galaxy. And since that time, this has been repeated a number of times. I forgot to put in the exact reference. This was just in September. For both Sagittarius A Star and now M87, I wouldn't say that this is routine, but at least it can be repeated and has been repeated a number of times and will continue to do so. All of this data has been taken with 3 stations. Okay, one in Hawaii, one in California, one in Arizona. Okay, but there are a lot of ways that the Event Horizon Telescope is going to be getting better in the future. First is by making these individual stations better, making them more sensitive, including more telescopes at each site, increasing bandwidth, et cetera. But I think the real changes are coming by adding new sites, and most important of which is ALMA. This is this very powerful millimeter telescope down in Chile. And the reason why this is especially important for an interferometer is that the signal-to-noise ratio, the sensitivity of any baseline, is dependent upon the sensitivity at either end. In fact, it's the geometric mean between the sensitivities at each end. So having a very sensitive telescope down here, a very sensitive station down here, makes it possible to obtain high signal-to-noise ratios on baselines to even not-so-good sites, even not-so-good telescopes. So you can, for example, talk about adding telescopes in Massachusetts, which is not known for its high, dry weather. Okay, so ALMA is going to make everything better, not just add another site. And of course, there are many other telescopes you might add. Many of them are already in the works. And if somebody gave us a large amount of money, there are ones we could think of adding in the future. But just to make the point that we're adding a number of sites, we're really going from being just a handful station interferometer to a many station interferometer, and that means we're really talking about making an imaging instrument. So here's a input theoretical image. This black business here, this black thing is a shadow. That's that silhouette from the horizon. And this is the reconstructed picture from visibilities taken with a 7-station array. 8, 9, 10. Start to get fairly high fidelity images. And you can certainly see that shadow. Okay, so really sub-horizon scale images. Unfortunately, we're not there yet. With only 3 stations, we have this sparse coverage of that Fourier transform plane. These points are where we've measured the Fourier transform of the image for Sagittarius A Star and for the second best case, M87. And you can see that these are essentially along a line, and that's just because of the east-west nature of the array. It has fairly short baselines in the north-south direction. Okay, so that means that we can't make an image yet. It wouldn't look anything like what the actual intrinsic image is. It would just be some ringing mess. And as a consequence, we see pictures like the ones I showed you a moment ago with these visibilities plotted in one dimension, essentially this dimension here along the long direction of the interferometer. Okay, and from that, you can robustly extract a size, characteristic size, just from the fact that these are lower than that. And that seems sort of unfortunate in comparison to the detailed questions I posited before. How do we convert this size measurement into information about these questions? And the answer is by putting the Event Horizon Telescope into a broader context, a context that involves theoretical understandings, theories on how accretion flows work, how jets form, even general relativity, as well as using other empirical priors, using information about spectra, using information at longer wavelengths, etc. Okay, and it's in the context of these other priors that we're really going to be extracting the most detailed information, the answers to those questions. And in fact, in the rest of my talk, what I'm going to talk about is exactly that. In 4 case studies, if I have time, more likely 3, how exactly we're getting answers to those detailed questions by adding the additional physics that we think we know and understand. All right, so the first has to do with whether or not black holes actually have horizons. And the strongest case that can be made to date is for Sagittarius A Star. So here's this picture I showed you before, this near-infrared image. You can't see the source at all. That was a little bit of a wavelength bias. If I were to show it to you at centimeter wavelengths, it really is a whopping source. That's not a marker showing you where it should be. That's really how bright it looks. And the reason is pretty simple. There's this non-thermal spectrum, which peaks around a millimeter and then turns over. Okay, so it's characteristic of many AGN. It's flat radio non-thermal spectrum. And this is not terribly bright, about 10 to the 36 ergs per second, so it gets drowned out by brightest stars. But nevertheless, for many reasons, it's thought that this arises primarily from accretion, that it's accretion powered. And I could give you a story to try to convince you of that, but let me just start with that assumption, that this emission is due to accretion. Okay, and that has strong implications for whether or not there can be a horizon. And the reason is we have to understand, or to understand why, we have to understand a little bit about how accretion works. I recently, 5 years ago now, moved to Toronto, and one of the first things we did was go up in the CN Tower, one of the tallest structures in North America. Torontoans are very proud of their CN Tower. And when you go up to the top, you find it's filled with school-aged children who are all dying to become young Galileos. And were they to get their wish and throw a penny off the top, they would see it accelerate down, converting gravitational potential energy into kinetic energy. Of course, that's not really what they would see. Some might be disappointed when the penny reached a terminal velocity. And the reason why it does that is because it's turning the additionally liberated gravitational potential energy into heat, both in the penny and in the air. And this heat is exactly what the luminosity from accreting sources is. Were this penny to drop far enough and fast enough, we would see it glow. Now, even though we see asteroids glowing in the atmosphere all the time, on an absolute sense, stuff falling onto the Earth doesn't really release a great deal of gravitational binding energy before it hits the surface, at least not in terms of its rest mass. On the other hand, were it falling into a black hole, it could release much more, simply because black holes are small. Okay? And so the luminosity from accretion power is really a statement about how much stuff is falling in. All right, so the story of accretion luminosity is really a story of mass accretion. And there's a coefficient that we don't really understand, but it's radiative efficiency, something like 10% for quasars. We think it's as low as 0.1% for Sag A Star, but I'll come to that later. Okay? But this is just a coefficient that relates mass accretion to luminosity. And it's really just about throwing pennies off of large towers. So, if that's why things shine, it turns out that accretion onto objects with horizons and objects without are qualitatively quite different. So when we talk about accretion onto a black hole, stuff falls in, heats up, shines, and then it redshifts away at the surface, at the horizon of the black hole. And that means the only emission I see is stuff that's binding energy that's liberated while the stuff was outside the horizon, and then that's it. Whereas accretion onto something like a neutron star, a very compact star, size just a bit more than its Schwarzschild radius, looks very similar at first. Stuff falls on, heats up, but then it splatters on the surface, and all the remaining kinetic energy that it had accrued by that time is deposited on the star and heats up the star. So that means not only is there this initial accretion luminosity bit, but now everything else gets out as well. Everything that didn't go into radiation or maybe go into powering outflows or anything else you can imagine. Okay, this additional surface luminosity associated with heating up an object, heating up a photosphere that we can observe. And this is in fact seen. If you look at the luminosity of neutron stars versus black holes at similar accretion rates, the neutron stars are 2 orders of magnitude brighter. And the reason is a thermal bump in their X-ray spectrum as a consequence of heating up the surface of the neutron star. Now for a neutron star, the reason why it heats up is baryonic physics, but for something like Sag A Star, we can make a much stronger case for why it's thermal emission. And to do that, imagine that we took Sag A Star, took it out and replaced it with something that had a surface. It could be a very high redshift surface, very compact surface. This doesn't mean that I built a surface around the horizon. Maybe general relativity is just wrong and we have something small down at the center. I don't know. All that matters is that there's a surface at high redshift. If that's the case, and I start emitting photons isotropically, most of them get lensed back onto the surface itself, and a handful escape. And we have a name for that. That's really a black body cavity. It's a perverse inside-out version of a black body cavity, but we still have a situation where most of the photons bounce around on the thing, and only a handful get out. And so I'd expect these compact, high-redshift surfaces to be generically black bodies. And that means I can go take a spectrum of Sagittarius A Star. Here's the radio spectrum and the infrared flux limits. These are not thought to be quiescent emission associated with the accretion flow itself. And I can plot on top of that the black body emission that I would have expected given its accretion rate, and assuming a 10% radiative efficiency. And that's 2 orders of magnitude above the infrared data points, the infrared flux limits. So this is rather clearly excluded. Okay, it sits above what the emission should be of everything from the accretion on the Sagittarius A Star. Now I cheated a little bit. I assumed a size. Were I to make it big, not only would my story about thermal emission not hold, but I could make a big thermal surface that's very much colder and still got rid of as much energy as it needed to. That is to say, I could move it down in temperature to this gap at terahertz frequencies. Okay, so in order to make this story clear, really robust, I need to have a size constraint as well. So I can make all this a little bit more robust by plotting things in a way that don't depend upon unknown or inferred quantities like mass accretion rate or assuming anything about GR. I can plot it in terms of direct observables, a ratio of surface luminosity to the observed luminosity, and a ratio of the apparent radius, how big the object looks to us in units of its distance, or equivalently, instead of luminosity ratios, those efficiencies. Okay, we don't really know what they are, but at least they're produced by physics that we can reproduce in the lab, so we think we have a handle on how big they could be. And this black line is that flux limit. Okay, this is the combination of limits for which that thermal bump would be above some of those infrared data points. Everything above that black line is just too bright. We would have seen it, and we don't. And then here are those size constraints, even from that one-dimensional fit that gave us a 40 microarc second size. Okay? Those size constraints mean that everything to the right are too big. So if you want to live in a universe without black holes, this is the corner of the parameter space you have to find a way to make peace with. You have to make very small and also very efficient, 99.6% efficient accretion flows. That is, 99.6 of the energy has to be extracted before it touches down. It's really like a feather alighting on the ground. And this is so far and above the 10% that we think applies to quasars, and certainly way above the 0.1% that we think applies to Sagittarius A Star, that this is really becoming absurd. So does Sagittarius A Star have a horizon? Well, it probably does. I mean, I work with a lot of very creative theorists. They might find a way out of this, but for now, they have to include at least 2 or 3 tooth fairies in any of those models. So we're really constraining the parameter space on which non-horizon types of models could exist. So already we're getting to fundamental physics answers about the natures of black holes, just with this one size constraint. All right, the next thing I want to talk about is information about Sagittarius A Star's accretion flow in a little bit more detail than the penny off the tower model. So I already showed this picture. I mentioned that this was small. It turns out that this is about the luminosity of a B star, not even an O star. And then that starts to give you feelings of inadequacy. But is that really low for an accreting black hole? Well, to consider that, we turn back to our understanding of accretion. So I told you before, accretion luminosity is really a story of how much you can accrete modulo this radiative uncertainty, radiative efficiency, uncertain radiative efficiency, which is related to the rate at which gravitational binding energy is released and subsequently radiated, and that's really quite important for something like Sagittarius A Star. But this means luminosity is related to how much you can accrete. And there are 2 important scales for how much you can accrete. One is the supply limit, the Bondi rate. This is how much you can accrete, or how fast material diffuses into the sphere of influence of the black hole. Okay, so it depends upon the mass of the black hole squared. Larger mass black holes can capture things further out. But it also depends upon the temperature of stuff. Higher temperatures mean that the stuff is unbound further in. Okay, so this is really a limit of how much you can get your hands on. And if I were to draw this Bondi rate in a log-log plot of mass accretion versus mass of the object, you'd get some line. Okay, and this line moves up or down depending upon the temperature. The second important limit is the demand limit, the Eddington rate. This is feedback in its first form. As the central source shines, photons from the central source scatter off of electrons in the accretion flow, impart momentum, and if it's bright enough, it actually blows away all the accreting material, and that implies, if we have a radiative efficiency from the luminosity, a mass accretion limit as well. If you accrete more than this, you stop your accretion flow altogether. And that has a weaker dependence on mass, so again, some line. And in reality, we're confined to live below this line. At sufficiently low masses, you're Bondi limited, you're supply limited. You just can't grab enough material. And at high masses, you're Eddington limited. Okay. Parents know this pretty well. If you feed your babies slowly, most of the food gets in. If you feed them too fast, it ends up on the walls. And it's exactly the same story. But this means that luminosity, which is a story of how much you can accrete, is now a story about how massive you are. For Sagittarius A Star, we have fantastic mass limits, fantastic mass estimates. And this comes from watching stars orbit the black hole at the center. So you can measure the mass of the black hole at the center of our galaxy the same way you measure the mass of the sun, by just watching individual stars. And that means we can write down a mass with two significant figures and be honest, those are really the significant figures. It's really a 10% or better mass estimate now, and that includes the systematic uncertainties. Okay, so it's really fantastic stuff. This is a movie from Andrea Gez's group at UCLA, but this is also being done by Reinhard Genzel here at MPE. Okay, and they both arrive at this 4.3 or so million solar mass limit. But at this 4.3 million solar masses, the Eddington rate is 10 to the 45 ergs per second. That's about 10 to the 9 times what's seen. So the luminosity of Sagittarius A Star is a billionth of Eddington. So it's definitely not anywhere close to being demand limited. We can also get a handle for that other limit, the supply limit, by looking at gas in the X-ray around Sagittarius A Star. You can get an estimate for the temperature and density, and based on that, there's a Bondi rate about 1/10,000th of Eddington. Okay, so that's certainly not supply limited either. So what's going on? I told you we have to live below this curve, but we're way below the Eddington limit, and we're still way below this Bondi limit. Okay, it's certainly not supply limited either. And the answer is that we've assumed, when we wrote down these limits, that Sagittarius A Star had a radiative efficiency similar to a quasar. If it doesn't, if it has a much lower radiative efficiency, it can still accrete large amounts of stuff, maybe not quite 10 to the minus 4 of the Eddington limit, but it can still accrete large amounts of stuff and still not produce very much radiation. Okay, and that's really the answer to this. As you get below about 10% of Eddington, the density goes down sufficiently that the coupling between the radiating electrons and the infalling ions, which being massive carry all the binding energy, becomes weak, and Sagittarius A Star becomes radiatively inefficient. Again, that might make you feel inadequate, but it turns out this is just average. It's the Copernican principle striking again. Our galactic center is not really any different from any other. It's like the 99% that aren't active. Okay. But this has a dramatic impact on its accretion flow. Because it can't liberate, it can't release this gravitational binding energy that's been released, it's roughly virialized. So it has pressures in the vertical direction that are comparable to the gravitational stresses and produces then thick disks. So the black hole at our galactic center doesn't like pancakes, it likes donuts. You think of this as a big fat donut, not a thin disk. Okay, so it's these thick disks. And this is just a consequence of having a hot accretion flow, having a weak coupling between the radiating electrons and the gravitational potential-bearing ions. So for this kind of accretion model, this thick accretion disks, you can add some Keplerian dynamics, okay, relativistic Keplerian dynamics, inside of an innermost stable circular orbit where no stable orbits exist in general relativity. It becomes ballistic and falls in. That can be quite close to the horizon in some cases. And there's some magnetic field. Simulations tell us it should be somewhere around plasma beta of about 10, so maybe a third of the equal partition value. and the electrons, which are not coupled to the ions. So I say thermal in quotes, but electrons that do the radiating. So there's some peaked distribution at lower temperature than the ions, and a power law high energy distribution, just like relativistic electrons in the corona of the sun. Okay? And with these models, doing the radiative transfer, putting in gravitational lensing, you can make pictures that look like this. So this is an accretion flow. It's orbiting around an axis that's vertical and in the screen. Okay? The side coming towards us looks bright because of Doppler beaming and Doppler shifting. And the side going away looks dim for exactly the same reason. And you see the characteristic shadow caused by gravitational lensing of the black hole. And in fact, you can also see on this side, the edge is a little obscured. And that's because on this side, it's a little optically thick still. Okay? And so we can make pictures like this, and they're parametrized by 6 numbers. 3 numbers which have to do with the normalization of this rather uncertain electron component, and 3 numbers that have to do with the spin of the black hole, the vector spin of the black hole. Of course, these numbers aren't all independent. I mentioned earlier that we have empirical priors, and one of those is the spectrum. And so any model we might consider for Sag A Star has to be able to reproduce the spectra. Okay? And that means we can fit out some subset of these by requiring that these models also fit the spectrum. And at the end of the day, we can make a library that just depends upon the spin. So from low spin to high spin. And these are spectrally fit models. Also depends upon the inclination. That's not shown. Okay? So we can have a bunch of input models for what in a reasonable, physically reasonable accretion flow looks like, and those are sensitive to things like the spin magnitude and direction. And then we can compare that directly to the Event Horizon Telescope data. You do this by starting with some intrinsic image. You worry a little bit about those intervening galactic electrons, which scatter broaden the image, blur it a little bit. You can compute the visibilities that are directly observed and compare in the visibility plane. And when you do that, you get a reduced chi-squared, a bit less than 1, sufficiently less that I called up my friends who actually make the Event Horizon Telescope work and asked them just how much were they fudging their errors by. And it turns out by the right amount. They were adding a 10% systematic uncertainty, which if you take out, we get a reduced chi-squared of 1. Is that big? I don't know. Certainly a good fit exists. But to assess whether or not that's really good, or if it's just maybe easy to fit, you can think about other models, models that don't have any physics in them, phenomenological models. In this case, because this looks kind of like a stretched blob, one of the things we tried was a stretched blob. It's just an asymmetric Gaussian. You plug that in and go through exactly the same process, you get a reduced chi-squared. That's a bit larger. How much larger? It's larger by the chi-squared is larger by about 8. Now, this alone isn't enough to say that one model is better than the other. Okay, for that, there are various statistical ways to compare them. Things like Bayesian information criterion or Colloquium information criterion, entropic methods, etc. It turns out that this is significant. This is sort of a 2.5, almost 3 sigma difference. Okay, so I can say with confidence that the physics mattered. Somehow, by plugging all that physics into making that previous picture, I did better by a statistically important measure. Okay. And you can do this not just for a stretched Gaussian, you can do it for any number of other phenomenological models that radio astronomers like to use, double point sources, annuli, symmetric Gaussians, all kinds of different things, and you get the same result. We always do better with the physical model. Physics matters. And if you wanted to push that further, you could assume that model was right and do some parameter estimation. And here's our best guess right now for the spin, direction, and magnitude for Sag A Star. Here's a picture of the probability distribution in spin magnitude space, inclination, so how far off the line of sight the black hole's spin is oriented, and each panel shows a different orientation on the sky. 0 would be north, 90 degrees would be 90 degrees to the east of north, so east. Okay? And already we're constrained to live on this very narrow sliver of this parameter space. So that looks sort of impressive. And when people ask me, have we seen a picture of this shadow yet, I would say in some ways, we have. Okay? We have this amazingly well-fit model. But if there's anything I'm really sure of, it's that our model is wrong. I mean, it's a very simplified model we're using. It's a semi-analytical model. It's a power law model. I mean, surely nature's more complicated. And so that means one of two things. Either the data was easy to fit, but I already argued that wasn't true. And the other one is that maybe the non-accretion physics, the physics that I might believe a little bit more, is the physics that's doing the job of making it fit. And that would be general relativity. That would be the gravitational lensing. Okay. Now, the nice thing about the Event Horizon Telescope is it's going to be self-validating. I mean, this whole RIAF, this whole accretion picture that we think is important for Sagittarius A Star, this inefficient, radiatively inefficient accretion flow solutions that are important, necessarily have thick disks. I already told you that earlier. You can't have thin disks. But the pictures that you get for one or the other are very different. So we're going to be able to distinguish these. We may already be able to distinguish these. We're just developing the capacity to do the statistical analysis. I also predict that the accretion flow should be subcapillarian. So stuff should be spiraling in rather quickly. And again, that's something we can directly test. So that's kind of exciting. We'll be able to tell whether or not our RIAF model not only fits the data we see, but whether or not it even makes internal sense. And if you wanted to really test accretion physics, find out how fast angular momentum gets transferred, how fast stuff can move from large scales to small scales, you might wish somebody would throw a blob into the galactic center. And it turns out that that's what's happening. In 2002, blob was out here. 2011, it's there. It's on a nearly radial orbit. This is from Stefan Gillison et al. Okay, this is almost enough to make you believe in providence. Just when we have the capacity to see stuff accreting, stuff is accreting. And 2013, next year, it's going to make its periastron passage. After that, for many, many years, stuff should rain down from the back of this gas cloud onto the galactic center. And that could produce enhancements in the accretion rate of roughly a factor of 2. And those kinds of enhancements are, again, easily visible. This is our current best guess of what it would look like, or what it looks like. That's at half the accretion rate. That's at twice the accretion rate. Okay, so we should be able to measure how long it takes this material after periastron to get down and then infer something about how material moves from large scales to small scales in realistic accretion flows. All right, so in light of the time, I'm going to skip lens theory and precession, and I'm going to jump right to the physics of jet launching, because it gives me a chance to talk about M87. And in astronomy, when you have two objects, you have a statistical sample. Now, in many ways, M87 is really very much alike Sagittarius A Star. They're very similar objects. It's very sub-Eddington. It's one of these radiatively inefficient sources, just like Sagittarius A Star. It shows a spectral break right around 1 millimeter. If I plot the spectral energy distribution, right around 1 millimeter, it starts to turn down, and that suggests it's become optically thin there. It has somewhat similar physical characteristics, physical scales. The inferred electron densities, inferred magnetic field strengths, with a bit of hand waving, turn out to be similar. I'm not sure why that is. It just happens to be that way. And frustratingly, it has very similar visibilities, the Fourier transform of the image. If I didn't tell you which one of these pictures is M87, you probably would have a hard time telling. On the other hand, M87 and Sagittarius A Star are very different in some ways. M87 has this clear extended radio emission associated with a relativistic jet, and Sagittarius A Star has none. These gray bars are the same distance in Schwarzschild radii. Okay, so if there was an M87-like jet in Sagittarius A Star, you would easily see it. Okay. And that means the kinds of models that I would consider for Sagittarius A Star and M87 have to be different. In M87, I need to be thinking about this radio jet. And there's a canonical story for how these radio jets are launched now. They tend to involve electromagnetic forces extracting black hole spin, or maybe angular momentum from an accretion flow. This is all done through large-scale ordered magnetic fields that get twisted up by whatever's holding onto them down near the bottom. And at least the jet part has a characteristic canonical force-free structure. Okay, it's dominated by the electromagnetic forces in the jet funnel. And that means I can, I should point out that this is a simulation by John McKinney. Simulations are expensive and hard to do, but nevertheless, it actually works quite well. You get the right characteristic run in jet widths as a function of distance from the radio core, and that fits the data out at large radii as well. And the size limit inferred from the recent Event Horizon Telescope. 'Telescope" observations would put us right down near the Schwarzschild radius. Okay, Now, doing simulations is hard and complicated, so it would be nice to have a cartoon, semi-analytic cartoon, and luckily you can do that. Because the particle inertia is irrelevant, it actually simplifies the problem quite a bit. You don't have to do magnetohydrodynamics. You can treat it in this force-free approximation, which almost makes it a graduate student, intro grad student problem. The one thing that we need to add are boundary conditions down near the black hole or near the disk, whatever's twisting the field lines up. And usually that's done by putting in an angular velocity for the magnetic field lines, which are presumably frozen to something. Okay, and at zero angular velocity, you just get colloidal field lines. As you increase that angular velocity, they twist up more and more. The more twisted they are, the faster the flow accelerates along the jet. And so how fast it gets, how rapidly it gets, is really a story of how much you've twisted it up. Okay? And so choosing these boundary conditions is just down to determining how fast stuff is being twisted around, either by frame dragging from the black hole or from an accretion flow around it. Okay. So it turns out that this kind of very simplified model does a good job of mocking up the simulations, even quantitatively. The content of this picture is the red line. In both cases, this is the maximal velocity line. Okay, and they both look parabolic. And this black line, which is a contour of fixed Lorentz factor in the outflow, and those black lines match up over there. So even with this very simple cartoon picture, you do quite well in reproducing the jet simulations. And so to apply this to M87, let us imagine that it's the disk that's twisting up the magnetic field lines. Now, I said that this is the disk and the black hole spin can both do it, but if you think black hole spin is twisting up magnetic field lines, you've already assumed, you've already bought into the idea that black hole spin is important for jet production. So let's pretend that's not the case, just to see if we can constrain it. And it turns out that then the only other source of angular momentum is the disk. Okay? And the maximum rate at which you twist things up then is related to the characteristic angular velocities at the inner edge of the disk, this angular velocity at this innermost stable circular orbit. But this angular velocity depends upon black hole spin. Rapidly rotating black holes twist this up very quickly because they have small innermost stable circular orbits, and therefore high angular velocities there. And that means they accelerate fast and have characteristically smaller images. And you can see this explicitly where low spin black holes have more slowly accelerating jets and therefore larger characteristic sizes in their images, and high spinning, rapidly spinning black holes have smaller emission regions associated with their more rapid accelerations. And so we can use the size constraint to constrain which ones of these models we're looking at by relating the emission region size to something having to do with the size of that innermost stable circular orbit. And when you do that, so either for a face-on or an edge-on, so face-on is green, edge-on is black, estimate for the lensed size of that innermost stable circular orbit, the current size limit puts us at a moderately spinning black hole at least. So even if you wanted to believe that spin had nothing to do with jet production, you're driven to the conclusion that at least the black hole has to be spinning. Right? And we have two cases now where we can look at horizon scale resolution or horizon scale structure of these objects. And the one in the center of our galaxy, which doesn't have a jet, seems to be spinning slowly. And the one at the center of M87, which does have a jet, has to at least be spinning moderately. And this is really the first empirical evidence that black hole spin has anything to do with jet production. Okay, so already we're starting to get at the connection between the properties of the black hole and the production of jets, these kinetic outflows. All right, so let me just make a few concluding remarks. I hope I've convinced you that we're already at the stage where we can start talking about resolving black hole horizons, that the Event Horizon Telescope exists and is taking data, and we're even able to do some science with that. And the way we're getting at some of those very detailed questions is by combining the outputs of the Event Horizon Telescope and complementary data sets and theoretical input. Okay? And that means we're getting to questions like whether or not horizons exist. We already see evidence of strong gravitational lensing at the level you'd expect from GR. We're already testing accretion models, and we're already establishing the spin-jet connection in a real source. And all of this is, of course, getting really exciting in the coming years. Thank you.
Okay, so
that is definitely true. They wanted it to be a very high spin. And that was dependent upon identifying an orbital timescale with some timescale in the flare. It's possible that the systematic uncertainties in the accretion flow modeling will drive our spin estimates up. I think that's going to be somewhat difficult. So right now, let's say that there's tension. And it will be, one of the things that we'll be able to do is look for variations in the structure of the source associated with the flaring emission. Okay, so I've actually been involved in a number of studies on how exactly we would do this in practice, and we should be able to do that quite well. And so if we find that there's a substantial amount of structural variability commensurate with those infrared flares, and I think that would really put those kinds of measurements on solid footing. But until you have that, there's always the question of what time scale really are you measuring when you look for that variability.
What's the time scale? Can you get this point in 5 minutes or something? I mean, these flares.
So the period at the ISCO is somewhere around half an hour. So even for a rapidly spinning black hole, 20 minutes or so. The visibilities are estimated on 10-minute chunks of data. With ALMA, that can be pushed down a bit. Really what we would be looking for would be variability in closure phases, which is some phase information about the image which tells you something about the changes in the structure, the intrinsic structure. And that we should be able to get on those 5 to 10 minute time scales. So we should be able to do that.
That was a very nice one, so thank you. I was wondering whether you can do something useful with stellar mass.
Now I understand the preface.
The sentence continues. With stellar mass black holes. I mean, you focus on the galactic
Yes.
black holes, supermassive black holes, but there must be many, many nearby black holes with 10, 20, or whatever solar masses. Maybe they are not accreting, but can you do something? Can you do some measurements the way you described it here with those guys as well?
So the answer is twofold. So first, stellar mass black holes are on average about as far away as the galactic center. Right? There's about 20 galactic stellar mass black holes known, and so at best they're maybe a factor of a few, 5 or so closer. And they're all 10 or 100,000 times less massive. So the angular scale associated with the stellar mass black hole is measured in pico-arc seconds. So I thought I was probably pushing it when I started talking about micro-arc seconds. So I think for that's what the people who want to do X-ray interferometry want to do. And I'm not really sure what the status of that is, but I know millimeter interferometry and infrared interferometry are hard enough. The second answer is there are supposed to be a lot of stellar mass black holes around the supermassive black holes at the centers of galaxies. And one thing that the Event Horizon Telescope should allow you to do is micro-arc second precision astrometry, absolute astrometry on Sagittarius A Star. And that's really important because at that level, you need to know where the black hole is. And you see that silhouette, you see the silhouette here, I know exactly where the black hole is. Okay, so fluctuations in the emission don't kill me when I do that. And so at microsecond astrometry, you can start to see the jitter from that central supermassive black hole induced by the stellar mass halo, the stellar mass remnants. And so there you might indirectly be able to measure something about the density and structure of the remnant cusp around supermassive black holes with the importance to things like light. But directly, I think it's really very difficult.
I think the result from this Hawaii, California baseline is quite impressive. But the question, of course, is what is the future in this business? When can we get additional baselines in particular in different directions to get a handle on the form?
This is absolutely right. The spread in the north-south direction is not 0, and it turns out that's reasonably important for the fits, but it's pretty close. ALMA is really, I think, next. In the previous set of observations, they tried to use apex, so I think Max Planck was heavily involved in this. And for various reasons that didn't work the first time, I think they tried again. I'm not positive. But ALMA, absolutely, we should they should be able to get detections on the north, those long north-south baselines. And it, millimeter VLBI was written into the ALMA science case. It's part of the standards for the correlators. So this is happening. Shep Dolman, the guy leading the observational effort out of MIT Haystack, he's spending his sabbatical down in Chile getting ALMA working with the Event Horizon Telescope. So I think in the next year or two, we absolutely expect to have data on those long north-south baselines.
So a chance to get data from the
Yes. Dan Maroney at Arizona successfully got an NSF grant to build a receiver. So the big problem with the South Pole Telescope is that it has a bolometer, which is no good for interferometry. So he obtained money to actually build a receiver for it. So that's going forward, and absolutely. I'm not sure what the timeline for that is, though. I know ALMA's coming pretty quick. I'm not sure about that. But yeah, that would be important.
Yeah, so you skipped lens theory precession, but what are the prospects for looking for that effect, and would you be able to measure the spin more directly through that effect?
Well, yeah. So that's the idea. So I can show it to you quickly. But this is exactly right. So already we have at least 4 epochs of data. They're separated by timescales of days to years. And in each epoch, we have data separated by timescales of hours to minutes to, in fact, 10 seconds is the shortest timescale that we probe. And on all of those, the parameters look the same. And you might think that if you had lens theory precession, that should create some sort of change in what we would guess the orientation of the disk should be. So here we've assumed in every case we've analyzed that the disk is aligned with the spin. But it turns out that that's not really a good approximation. And there was this nice movie by Chris Fagil, which shows this explicitly, that when you have thick disks, they're qualitatively different from thin disks in that you get this lens theory precession that precesses the whole disk together. And this is a simulation of exactly that. I don't know what this is, and I need to ask him what that is. I think that's just a visualization artifact. But you can see the whole disk turns around. And so you'd expect then, if this was happening in Sagittarius Star, to see a precession in the orbital, or in the disk parameters, in the disk inclination. Okay, so we can go look for that. Oops. There we are. And right now, how sensitive are we? We can tell the difference between this and that. Okay, so that's the wobble we can already exclude. There's a bunch of stuff on what lens theory precession is. Right, the time scale that you'd guess from that's about 2 years. We already see that. And the net result is, that means today, with the data we have, we can draw a posterior probability distribution after marginalizing all the other crap that suddenly having a tilted disk brings in. Things like the disk orientation relative to the spin of the black hole spin on the sky, all of that. You can get a probability distribution for the size of the disk, which is really the thing that limits how fast it precesses. That looks like this, and that should be getting better in the next year or so. So we could exclude disk sizes less than some amount by rather high amounts. This also translates into a good limit on the spin as well, like you said. But I don't have a picture of that, unfortunately. So that's getting exciting for that, too.
So the circular polarization towards the Sagittarius Star is sort of constant on 120 years, and that's very constant to many people, and some of them suggest that maybe a signature of sort of the spin of the black hole. And what's your take on this, or what is your latest?
I think it's interesting, too. The fact that it's been constant over so many years implies that you have to somehow relate that circular polarization to some pseudo-vector in the system. And I think spin is as good as any, but figuring out how to make it related to that's hard. I have a story I can tell, which is a detailed radiative transfer story. It doesn't depend on lensing or anything like this, but it has to do with an analog of Faraday rotation through sheared flows. But that's complicated. But I certainly think it's an interesting story that I don't talk about it a lot, or don't think about it a lot in the context of the Event Horizon Telescope observations. One, because we're just getting to the point where it's possible to think about doing linear polarization, which is interesting in its own right. Two, because I really do think that detailed radiative transfer is important to getting that story right, that we're just not doing here yet. But it's certainly an interesting thing. It's not just Sagittarius A Star. In fact, that's true of many blazars, that it has consistent signed, not just blazars, AGN as well, consistent signed circular polarization. So it might be an interesting signature if we can only figure out how to interpret it.
Yeah, you talked on observations in the millimeter range that the atmospheric windows are not very clean in these regions with residual atmospheric water vapor. Is this a problem if you image objects like the galactic center, which are very young in itself?
Yeah, so absolutely right. The wavelength of the observations are really 1.3 millimeters. So it's in the 235, 230 gigahertz window. And the next one will be 345, so the next highest atmospheric window. This does make the whole process much more challenging. So this is why when you think about where you put stations, you need to put them in the highest, driest sites. That's why people keep putting millimeter telescopes on the Atacama Plain, which seems good for them, but it's bad for us because we want large distances between them. It turns out that at 2:30, the weather's good enough at enough sites that you can do this, but you really do end up cutting out large portions of the potential observance schedule. Pushing to 345 will probably be possible to do it. At 690, which is the next window, I think the chance of getting good enough weather at most places, people have looked into this, and it's just too rare. So you're absolutely right that limits dramatically how often you can perform those observations. How does that change the variability? Well, this is why I mentioned before looking at closure phases. And one of the nice things about closure phases is that they don't depend. I mean, they are constructed specifically to be independent of phase errors at individual telescopes. And the primary cause of those phase errors is water vapor. So that's why you look at closure phases. After that, we look at primarily visibility magnitudes. And those tend to be less sensitive to the amount of water absorption. And of course, I'm a theorist in all of this. So I take visibilities as they're reported and try to say something interesting from those. The reason why I say I don't do data analysis is because I understand at the observer, at the background level, I understand how hard it is to take voltage outputs from telescopes and put them together to make these highly processed data products that I get my hands on and use. But there are other people like Shep Billman and others who actually get their hands dirty in doing all the calibrations. So it looks like they get most of those things out. Maybe you'd have to ask them for the details.
Okay, final question back.
This is, again, a very nice talk. I'm wondering, have you given any thought about how we might start observing high redshift supermassive black holes in the near infrared down to the, for example, during the evolution phase, or maybe 15 redshift 15 down to redshift 5?
So you mean with something like the Event Horizon Telescope, or you mean just generically?
Actually, I'm opening it wide up. I'm just curious what you thought about it.
I haven't thought about it generically. With the Event Horizon Telescope, we're really restricted by the fact that we're not, people aren't building new radio telescopes besides ALMA. And so you have sensitivity limits. And so we really can only look at bright sources. So for example, quite apart from high redshift galaxies, M31 is just depressingly dim. And so, at least for a number of years, we won't be able to do M31, which is next on the list. I would worry that high redshift galaxies would all be much too dim. And when I say bright, I mean Jansky level sources. Maybe we could get down to millijanskys if we really push it. But if you think that you could do better than that, I would be fascinated to hear about it. If there are either really bright radio galaxies at high redshift, or if there were a really clever way to do better. But beyond that, no, I haven't really thought much about it, sorry.